Hello, my name is Jack Lattanzi. Today I'm going to be demoing my Lab 8 accumulator-based tally design. I would like to share my screen with you to start. The overall idea was we had to build and design a tally unit using an adder subtractor from a previous lab. We have to design a register, and then we have to use our previous binary to 7-segment decoder from the lab before this and create a tally unit. So here's the looking into the design. We were given this design in the lab. This first, before we created this design, I created a register that is made of 8 negative edge triggered register, or it's a negative edge triggered 8-bit register using D flip-flops. This register has the ability to reset, which resets the number here, as well as as well as a clock which controls it. So the way this whole system works in the design, there's an 8-bit input that goes into the adder subtractor. This is the initial input, so it's added to nothing. It goes into here into the register, and it is stored there. It is stored in the register and brought out and put into this decoder, which has a ROM, which it uses to figure out the 3-digit output. The output's in binary, and then you can also see that this output from the register goes back around and is then again input into the next one. So then the clock tick goes by and we input another value and it's added to the previous value, so it's kind of a running tally, and we can keep doing this over and over again. Here is my design. My design is similar to this, except it is implemented into Quartus now. So the differences you can see is there's a clock going into the register like before. There's also a clock that goes into the display, the decoder. So the input comes in on a bus here and is inputted. It's added to nothing, goes through and it's stored here, comes out, it's displayed. The address line comes in here and the address is found here, and this corresponds to the 24-bit output, which 7 or 21 of them are used in the display and there's 3 padding bits. Okay, so then there is also the clear function here, you can see, which will clear the register and the whole system, which is stored in here. And the way it works, say we put in a 5 goes in, goes out displayed, 5 goes around, we put in a 2, the 5 and 2 are added, 7 is stored in here, 7 comes out, the 7 comes around, comes down. Say then at this point we would switch this input, the CN3, which is the function. We would change the function to subtraction by inputting a 1 here, and then we input a 1, and that's subtracted from the total and displayed here. The working of this design is seen here. Well, first, before I talk about this, our demo cases are 0 plus 1 with an answer of 1, then added 6 to that with an answer of 7, and then minus 3 with an end result of 4. I'll be using this image to back up that I have the right digit displayed and in the waveform. So the end time is 120 nanoseconds. As you can see, here's the input, each time. You can see that down here, there's a clock for the ROM, which is going in and displaying that address, and a clock for the register. Then the clear is set to 1, so it isn't constantly being cleared. And then here we go. All right, so here's the 24-bit output here. We start with the 0 input. 0 goes through, the clock tick hits here, and the 0 is activated. So we have 0, 0, 0 displayed. goes out to here, and then a 0 is stored, and then we input a 1, so then we go to here, we get that, and we get to here, and our output of 1 is right here. We can back that up because a 1 has all of them on except C and B. We can see that for a 1 here, all of them are on except C and B right here. So there's 1, C and B are off, and then the next ones are on. Then we add 6 here, and you can see that this is implemented right here because a 7 is very similar to show. Then a 1, a 7 has all those on, or is the same as a 1, but the A is off. So you can see here the A comes off and all the same ones are on to show a 7 correctly. Then you can see at this point here, once we're inputting this number, the cin function changes to 1 to make it subtraction, and we subtract a 3. The 3 is then subtracted and computed out to here, and our output is a 0, 0, and 4, which I can use to back up here, which it has the first 2 are off, next 2 are on, and then, or the first 2 are on, next 2 are off, next 2 are on, last one's off. So then we can see that is happening here to display a 4. I want to mention these first 8 bits up here with 1 padding bit are for the first 7 segment. Next 7 segment is the 1 in the middle, and then the 1 on the far right is here. So we can see for all these values, we would be displaying like a 0, 0, 0, 0, 0, 1, then a 0, 0, 7, then a 0, 0, 4. And you can see that 0, 0 is followed all through up these top 2. And then we have, go to here, we have 1, then we got 7, and then we have the subtraction happen, we have 4. So those were the demo cases right there. If you need another look at this waveform, this waveform has successfully proven the circuit is working and tallying correctly. The number, so the number goes in and it's registered and stored, and then its next number comes in, registered and stored, and then the next one, it keeps going. Thank you for watching my presentation. My name is Jack Lattanzi. I am in lab section 5 at 9 a.m. This has been my lab 8 accumulator-based tally unit demonstration. Thank you.